Danielle Applestone, and I'm a PhD student at UT Austin under Professor Manthram. And I would like to talk to you today about some nanocomposite alloy anode materials. These materials I'm super excited about because not only do they offer twice the volumetric capacity of commercial graphite, but it's stable for 500 cycles. So that's a little taste of what the talk will be like. Just going to cover the background of why we're studying these materials, how we characterize them, how they perform in batteries, why they perform so well, and then leave you with a few open questions that we're still working on. So the reason we want to study alloy anode materials is we're looking for an alternative to graphite. So a lot of alloy anodes, you can get a higher volumetric and gravimetric capacity compared to commercial graphite. Also, the potential at which these alloy anodes react with lithium is far above the potential at which lithium plating occurs, which makes them safer. Also, we're looking for some anode materials that are compatible with manganese spinel, something that doesn't suffer from the manganese poisoning that we see with graphite. And alloy anodes offer a lot of options in these categories. The one problem is that they suffer from capacity fade during cycling. So we wanted to figure out a solution to the problem of capacity fade. So we went and looked through the literature for alloy anode materials that we might be able to start with. We decided to choose the copper antimony alloy, Cu2Sb. It's been studied quite a lot, but we haven't really seen much above 60 cycles of stable capacity life in the literature, and the discharge capacity of around 300 milliamp hours per gram. So we thought that would be a good starting point and decided to try to extend that cycle life and maybe see if we could get an improvement in performance in terms of capacity. So we chose a different strategy. Instead of the typical copper metal, antimony metal, ball millet, we decided to use a mechanochemical reduction by where you take antimony oxide, aluminum metal, copper metal, and carbon, and you ball mill it. And so the reaction that makes this alloy here happens inside the ball mill. This reaction has a negative Gibbs free energy, so it proceeds spontaneously, and what you end up with is a material where you have this ratio between the aluminum oxide and the Cu2Sb is fixed. It's a stoichiometric relationship. What you can vary is the weight percent of carbon. We just chose 20 weight percent. Acetylene black is the carbon that we use for these materials. And what we found is a material with higher tap density than commercial graphite. Commercial graphite that we tested was from 0.6 to 1 grams per centimeter cubed, so we've got about a 40% increase in tap density, which translates to higher volumetric capacity over graphite. Also, our discharge capacities were 630 milliamp hours per gram in the first cycle and 410 milliamp hours per gram in the second cycle. And you notice that there's a difference there. Not all of that first cycle capacity loss is irreversible. In this test, we were studying from 0 to 2 volts, whereas the open circuit voltage for this material can be between 2.7 or 3 volts. So not all of that is irreversible. Most notably about this material, and what makes it excellent, is the 80% capacity retention after 500 cycles, which is considered to be stable cycle life. So we wanted to figure out what exactly we had made in our ball mill mechanochemical reaction. And when we looked at XRD of this material, this is the one with the aluminum oxide, we weren't able to see basically anything. This peak corresponds to, it's the same location for Cu2Sb, but it's very broad and not anything that we could really differentiate. Is this Cu2Sb or is this copper metal? And we also could not see any aluminum oxide from XRD. So we turned to XPS, and we found that this is the top graph here is the aluminum metal spectra for XPS, and this peak right here is for aluminum, and the binding energy does correspond to aluminum oxide. So we found, yes, we do have aluminum oxide in our material. And when we looked at the spectra for copper, we found that the shape of these peaks is more like copper metal, not like copper oxide. Copper oxide sort of has several different peaks. So we found that we didn't have copper oxide, and we also had copper peaks that were shifted to higher binding energies, indicating that they had been bound to something. It's not metallic copper. One other thing that we found when we looked at the antimony spectrum for XPS is that we had a small amount of metallic antimony impurity. So we have antimony that is bonded to something, and we also have a small amount of metallic antimony. So we looked at high-res TEM and high-res STEM to see if our particles were crystalline and maybe figure out what the structure was. What we found was from TEM that we had very small particles, spherical crystalline particles that were about 2 to 20 nanometers in size, embedded in this matrix of aluminum oxide and carbon. And when we looked at when we did a FFT analysis on our high-res STEM images, we found that yes, we do have Cu2Sb as our crystalline phase. The despacing's matched up with planes for Cu2Sb. So what we have is we have a material that is very small, spherical, crystalline particles embedded in a matrix of aluminum oxide and carbon. And so now you can see how it performs. Just a note, the current measurement that I have here is not in terms of C rate. That's because in order to calculate C rate, you need to know the theoretical capacity for your material. And we had variable amounts of carbon. We weren't sure how much that carbon was contributing to the theoretical capacity for our material. So instead of kind of arbitrarily choosing a C rate, we decided to just do 100 milliamps per gram of composite material, and that's the entire composite, Cu2Sb, aluminum oxide, and C, just to clarify what our current, what our charge rates are. So you can see 500 cycles, stable. This is graphite, the green line is graphite, that's commercial conocographite. And you also can see that when you compare this red line, which is Cu2Sb, C of a similar particle size, to Cu2Sb, aluminum oxide, and carbon, there's a significant improvement. Aluminum oxide is having a big impact on the cycle performance for this material. We also looked at, usually when you look at the voltage profile and you look at the corresponding differential capacity plot, you notice something that's a little bit strange. We have 3 peaks down here in the lithium insertion range, and we have 4 peaks in the lithium extraction range. And you might think that one of those peaks was like an irreversible reaction that was happening, but if there was a significant irreversible reaction that was showing up in this DCP, we might expect to see a cycle performance that wasn't quite as stable. So our thinking is that there is some sort of asymmetry in the reaction mechanism that's happening for this material. We also looked at the rate capability and high temperature performance for this material. You can see that even at a charge rate that's as high as 5 amps per gram of composite material, we still have a gravimetric discharge capacity that's around that for commercial graphite. The high temperature performance was not as great as the room temperature performance as you might have expected, but it was fairly stable for at least 100 cycles. We did a little bit of optimization of our material. This red line here is our composite material cycled between 0.5 volts and its open circuit voltage, which in this case was 3. We cycled between 0.5 and 3 so that we could show that yes, we don't have to discharge all the way down to 0 volts versus lithium metal. We can keep it in a safer operating range. What we found also is when we cycled in this range, we were able to reduce the irreversible capacity loss to around 80 to 90 milliamp hours per gram, which was a significant improvement. And this cycle test is still going, but we have 100 cycles of stable capacity, and it's definitely promising with that low irreversible capacity loss in the first cycle. We also have just started doing some full cell experiments, comparing our composite material, like pairing it up with manganese-containing spinel cathodes. This is a room temperature cycle test. We have some going now that are at high temperature, which will probably indicate more about our material's compatibility and resistance to manganese poisoning, but at least that's a starting point, indicating our materials might be compatible with those manganese spinel cathodes. So now the question is, why is aluminum oxide helping this material so much? And the first indication that we got of how aluminum oxide is improving this material's performance was from impedance analysis. So after you cycle this material even 1 or 20 times, you can see that compared to, okay, so like the blue is with aluminum oxide, the red is without aluminum oxide, and you can see that in all the frequency ranges, when you have aluminum oxide in your material, it is reducing the resistance to charge transfer. So big clue number 1 is aluminum oxide is improving the transfer of charge in this material, and that's obviously impacting the reversibility of the reaction that it has with lithium. Another really exciting bit of data for me was these are TEM images of electrodes that have been cycled for various numbers of cycles. The top row is with aluminum oxide, the bottom row is our alloy without aluminum oxide. And just skipping to the end here, this is the material, is the electrode material after 500 cycles. And you can see that these spheres here are crystalline particles, and they're still, even after 500 cycles, constrained to about their original size. They're still in the 2 to 20 nanometer range. And what's the most striking is they're separate from one another. They are in their own little zones, surrounded by this aluminum oxide and carbon. When you look down here, when you don't have aluminum oxide in your material, you see these particles are fused. They're stuck together, and this material, after 247 cycles, is not offering any capacity. It has catastrophically failed at that point. So, aluminum oxide is solving the problem of this agglomeration that ruins these battery materials, which is pretty exciting. So our big unanswered question for this material is actually pretty interesting to me. So what is the reaction mechanism? These particles are small, so when we look at them with XRD, if it's ex situ XRD or in situ XRD, we're not able to see the crystalline phases because the peaks are very broad, the particles are so small, we can't really, we can't differentiate phases. And so we also tried high-res TEM, and the resolution for despacing wasn't really enough for us. But we know that when we look at the literature, this is published data for, this is Cu2Sb that has been ball milled with carbon, and it's the most analogous to our materials. And we see 3 lithium insertion peaks, 3 lithium extraction peaks. Our material is different in a few ways, and one of the ways is the particle size. So also, if you compare, I just looked this up this morning, this is the same as this material. However, this has been ball milled, and it's about 30 nanometers in size. This one is about 200 nanometers in size, and you can see in the insertion part, there's only 2 peaks here. There's 3 peaks here, and when you go even smaller to our particles, which are 2 to 20 nanometers in range, you see 4 peaks. And I find that really interesting, and we like to figure out what the reaction mechanism is. We have a few ideas about it, what it might be, and our thinking is that maybe when you constrain these particles to a small size, when you extrude the copper and you insert the lithium, and then you have to undo that reaction, you have a very small particle that's surrounded by aluminum oxide and carbon, and that copper is not limited by its large size. It can go into and out of these small particles more reversibly than if the particles were larger. So that's kind of where we're at with this material. It's got this incredible cycle life due to not only the presence of the aluminum oxide improving the charge transfer, but also because of the small particle size that we think is fundamentally changing the way this material, this alloy, reacts with lithium. So I would just like to acknowledge my professor, Dr. Mantharam, and also a postdoc I work with, Dr. Yoon, and Dr. Chow and Dr. Yunichik for helping me out with the TEM, and also to acknowledge our funding source, the DOE. So if you have any questions, I would love to hear all of your questions and any ideas about the reaction mechanism you might have.